Hello everyone. I'm Srinivas Reddy. I'm the trainer for LPDDR5 5X technology training. In this short video, we'll be talking about the LPDDR5 training overview. We'll talk about the course syllabus, the e-learning, the mode of training, and the other course materials that are provided as part of the course. So let me directly take you to the our InSkill portal where LPDDR5 videos are present. Course is available for self-paced learning mode. Okay, so once you log in, you have access to the LPDDR5 course. So this has around uh, right now we have 87 lectures. These are spread across 14 units, and the overall duration should be somewhere around 30 hours, 30 to 35 hours, and it will increase. I mean, as we start covering each topic in more depth, that will increase. So these are the overall units. So once you log in, you have access to the videos, the presentations, assignments, notes. This course doesn't have any labs, so I'm still working on updating the assignments and the notes. Okay, coming to the video part, you see there are totally uh, 14 units here till this 14th unit. Okay, in that we have, as I said, around 87 videos are there. These 87 videos start off with, I mean, let's go by video unit by unit basis, so that will give us a good understanding of what all contents have been covered. So it starts off with LPDDR5 overview, the pad definitions, the bank architecture, the addressing. I mean, how do we address different configurations of LPDDR5, and what are the different speed grades in LPDDR5 and the different bus sequences. So the corresponding lectures are present in this unit. Okay. We also talk about W clock, clocking implementation in LPDDR5. The next unit talks about the state diagram and the mode registers. For each of these video, you can see the, I mean, each of these lectures, you can see the which video, you can watch that corresponding video, and the presentation is also available specific to this session. So it may take little time because the LPDDR5 presentation is quite big, around 800 to 900 slides. Around 826 slides it has got. It may take little time for it to load. But for each of these videos, the corresponding slides have been updated here. So let's wait for a moment. So in the meantime, you don't need to really continue to wait on this. You could actually be going through the other lectures. You could be even watching this lecture, and in case you want to parallelly go through the presentation, you could load it. Okay. Typically, it takes the time for the first time because this how our website works is it tries to load the entire LPDDR5 presentation. From that, it tries to get the slides. So hence, it may take little time, but once it is loaded, since it will be in the cache, so it may not take much time to load the other slides. Okay, so then this unit talks about the LPDDR5 state diagram, the different mode registers of LPDDR5 and 5X till all the mode register 72. Then the next unit talks about the command truth table, the write and read operations. So where we have the command truth table, WCK to CK synchronization, and different operations like row operation, burst write, read write latency, write recovery time, mask write operation. Then continuation to that, it will talk about the next set of commands like refresh operation, optimize refresh, self refresh, partial array self refresh, and power down, deep sleep mode, all other operations. So this unit 3 and unit 4 essentially covers all the different commands of the LPDDR5. Then unit 5 talks about the frequency set point, um, Okay, undetermination and the asynchronous non-target ODT mode, all those things it talks about. It is more deep into ODT as such, all the sessions of this. Then the unit 6 talks about the concept of clock stop and frequency change in LPDDR5. Then we also talk about VREF current generator, the thermal offset temperature sensor, and the multi-purpose command. So these all sessions focus on, that is session number 38 to 42, focus on these aspects. Then the next one is about interval oscillator. There is one TWCK22DQX interval oscillator, which talks about the oscillator matching error and oscillator readout timing and how LPDDR5 controller implements these things. Then we have next unit talks about low power functions like DVFS, dynamic voltage frequency scaling, the data copy feature, and the write X feature. Okay. The next unit talks about all the different types of trainings in LPDDR5 technology, like how the initialization and training is implemented, VDD to rail setting, and it also talks about GQ calibration basics. So where we talk about all the aspects of GQ calibration, right? Starting from command-based calibration, resistor sharing, GQ reset, then multi-die considerations. It also talks about command bus training mode, all the trainings you could see, the duty cycle adjuster, DQ, read DQ calibration, WCK DQ training. So everything it talks about. So we cover all the different aspects of the LPDDR5 training. Then unit 10 is focused on post package repair. Okay. Then unit 11 is focused on refresh management command. So what is refresh management command, management threshold, and what are the refresh management enhancements. Then unit 12 is focused on link decision feedback equalization, link ECC check matrix. Then the unit 13 is focused on single-ended mode, enhanced WCK always on mode, and pre-emphasis for DQ output. The unit 14 is focused on the mostly the timing parameters, rank to rank AC timing, and common constraint timings, and read to write timing command constraint. I mean, various timing constraints it is focused on. So this is how entire course has been spread. It touches upon the basics of LPDDR5. Initially, it starts off with, as I mentioned, it starts off with the enhancements. I'll in continuation to this demo, I'll just give a brief about what are the enhancements of LPDDR5 over previous generations of LPDDR, and we'll also talk briefly about what is LPDDR5. In this lecture, let us discuss about the enhancements that have happened in LPDDR5. As you are aware, LPDDR5 is the fifth generation of the LPDDR series, that is the low power DDR RAMs, SDRAMs. So one of the enhancement that happened is the increase of the speed per pin. It has been increased to 6400 megatransfers per second, which is essentially 6.4 gigabits per second per pin. So whereas LPDDR4 we would get 3.2 gigabits per second per pin, and it has got new low power features added. We'll be talking in depth of each of these features in the further lectures. One of the thing is LPDDR5 operates at 0.5 to 1.1 volts with advanced power saving modes. I mean, when you are putting in advanced power saving mode, it can work at a low voltages, whereas LPDDR4 operates at 1.1 volt. So you can see the reduced operating voltage results in a low power consumption, and it also has something called deep sleep mode, which was not there in LPDDR4. It helps reduce the power consumption when memory is not actively in use. And it also has two new commands added to help power consumption by reducing the data transmission. One is called as data copy, which allows data to be copied from one IO pin to another without transferring data to the entire memory chip, which essentially reduces the power consumption. You don't have to drive all the pins. There is a provision where we can copy data from one pin to other. Okay, that will essentially reduce the amount of pins that you have to drive in specific scenarios. And then there is something called write X command has been introduced, which eliminates the need to send data from SoC to LPDDR5 chip during the data transfer, further reducing power. So we'll talk more about these commands as we go forward. Then it has got dynamic voltage frequency scaling for core and IO. And it also has selectable differential or single-ended clocks and read data strobes. And partial array self-refresh and auto refresh are there. Other than that, LPDDR5 comes with larger densities. That is, LPDDR5 supports up to 32 gigabits per channel. So that much density it can have. Whereas in LPDDR4, it has only support up to 16 gigabits per channel. The architecture is LPDDR5 supports multiple bank architecture. When it supports bank group mode, 16 bank mode, 8 bank mode, whereas LPDDR4 there was only one architecture, that is 16 bank architecture. And it has got a new multi-clock architecture which is not there in LPDDR4, which allows for separate it synchronous clocks for data and address command and control. So there will be a separate clock used for data purpose, separate clock used for address control and command and control purpose. It actually simplifies the overall development process. It improves the synchronization and reduces the clock skew. And it also has some features added for RAS, that is reliability, availability, and serviceability. And some signal integrity techniques have been introduced, like something called NT-ODT, non-target DRAM termination, and which helps minimizing the signal reflections and ensuring proper termination at the memory interface. It also has one tap DFE, decision feedback equalization, has been added. I mean, one tap means kind of one stage DFE. DFE helps in mitigating the inter-symbol interference. And also receiver equalization and transmitter pre-emphasis feature has been added, so which helps in shaping the signal to compensate for the channel impairments and ensure proper reception. So basically equalization is a concept where the transmitter will use some parameters how the signal should be transmitted, because whatever we are sending, even though we are sending as ones and zeros, but finally we are sending it as an analog signal, right? So how the analog signal should be sent, what should be the pre-emphasis level, I mean how the signal should be sent, something like this, what should be this value, what should be this value, what should be this value. So those are decided through some coefficients. So there will be such receiver equalization will be there, some transmitter pre-emphasis will be there, so that ensures that signal whatever is coming will be captured properly. So these are the enhancements. And the LPDDR5 is majorly developed for target applications like mobile phone and tablet market, and it also targeted for automotive applications. Let us now understand how the LPDDR5 has evolved. Uh, it is a standard designed to, basically LPDDR5 as you know is a standard designed to dissipate very low power when the memory isn't needed by the end device. So that's the primary requirement, because the there is other side of the DDR is the PC DDR, the one which is used for personal computers. LPDDR5 is mostly meant for the portable applications and the mobile kind of applications, mobile tabs. Okay, it comes with the smaller bit bus, which is one of the factors that helps reduce the power consumption. Compared to DDR, the low power standard makes it easy to quickly throttle performance up and down as it operates at a lower frequency. By going into low power state when the end device isn't being used, LPDDR5 enables significant power savings. So there is a power saving states. When you are not using it, immediately goes into power saving states and helps with the power savings. Compared to DDR4, LPDDR4 offers reduced power consumption but does at the cost of bandwidth. I mean, of course, LPDDR4 doesn't give the bandwidth on level of PCDDR. LPDDR4 has a dual 16-bit channels resulting in 32-bit total bus. In comparison, DDR4 has 64-bit channels. I mean, you are essentially reducing the bit bus, and which is one of the factors that is contributing to reduced power consumption. The LPDDR4 improves the data rates by almost double when compared to previous generations. I mean, that has been the primary requirement of every DDR new generation. LPDDR3 gives 1600 Mbps, LPDDR4 gives 3200 Mbps. LPDDR3 had only one channel, whereas in LPDDR4 we have two channels, each giving 16 bits of data, while LPDDR4 offers a two channel design. So what is the advantage is it offers you 16 bits per channel, thus providing total of 32 bits. This can be helpful in lowering the power requirements of the core. The short data path, I mean, so that reduces the data paths by having two channels, ensures that the low power consumption. This can be quite helpful in improving the operational speed and the performance. LPDDR4 offers a marginal improvement in the power consumption from 1.2 volts to which is used in LPDDR3 to 1.1 volts in LPDDR4. Now let's briefly talk about LPDDR5X. So it is a latest upgraded version of the LPDDR5. It achieves higher data transfer rates than LPDDR5. It works at 8.5 gigabits per second per pin compared to LPDDR5's 6.4 gigabits per second. It comes with a better signal integrity enabled via receiver equalization and transmitter pre-emphasis. And it has got greater reliability. New adaptive refresh management feature has been introduced. So these are some of the factors that contribute to LPDDR5X working at higher speeds. X means extended kind of, you can think of. So this is a brief about LPDDR and LPDDR updates.
Will now be recorded.
So in this session, let us discuss about the major enhancements that happened in LPDDR5 with respect to LPDDR4 and LPDDR4X. As you are aware, LPDDR5 is released in two versions. One is LPDDR5 and LPDDR5X. So as you can see from the table, LPDDR4 was released in 2014, 4X was released in 2016, 5 was released in 2019, 5X is released in 2022. So the package type it used 200 FPGA, and 4X used either 200, 376 or 432, 556. Okay. LPDDR5 used 315 or 496 FPGA. 5X used 315, 441, 496. Uh, Transfer rate, LPDDR4 supported transfer rates of 4266 megabits per second. 4X also supported same. The only improvement that majorly that was done from 4 to 4X was with respect to the power optimization, where it was working at 1.1 volts. Now this was designed to work at 0.6 volts. LPDDR5 improved the speed to 6400 megabits per second, and VDDQ also is reduced from zero point 0.6 to zero point 0.5 volts. Coming from 5 to 5x, the voltage, the VDD1 is at 1.8 volts, VDD2 is reduced to 1.05 or zero point 0.9 volts, VDDQ remains at 0.5 volts. The power consumption, relatively high power consumption because the voltages are generally high, trading bandwidth for lower power consumption. The power consumption is reduced by around 17% compared to LPDDR4, and IO voltage reduced by 50%. That is this one, VDDQ. Okay. The power consumption reduced by 45% compared to LPDDR4 or 4X, introducing energy saving technologies such as DVFS. So here, dynamic voltage frequency scaling kind of technologies has been reduced, where the voltage and frequency be scaled down when we don't require the large amount of bandwidth. Again, 5x about 10% lower than the LPDDR5, improving device battery life. Coming to the speed, we have discussed this is the speed which the different generations of LPDDR5 can support. Given this speed, what is the bandwidth that we can achieve is shown here. 17.064 gigabytes per second, and basically you have to multiply it by 4. If you see, you have to multiply it by 4 because this is speed per pin. So if there are 32 pins, and when you are converting to byte, 32 divided by 8 you have to multiply. So 4, when you multiply, this will come to this number. When you multiply this with 4, it will come to this number, and you convert mbps to gigabytes per second, basically, because you are doing the 1000 division. The same thing shown here. So one more major enhancement that has been done in LPDDR5 is the new clocking scheme, which is significantly different from the earlier generations of the LPDDR. In the earlier LPDDR generations, a single clock from the host to device essentially synchronize the interface between the host and device. So we are only using one clock for synchronizing the interface between host and device. The clock used to set the transfer rate of the command and address signals. The clock also, same clock also fixed the rate at which data, that is DQ and data strobes, were transferred between host and device during the writes and device to host during the reads. That means both the address and command and the write data transfers were also decided based on the clock. So you see, you have the LPDDR controller, you have a clock which is generating the clock, the PLL is generating the clock. The same clock is used for DQS generation. So both clock and DQS pad were driven by the same frequency. So when this clock comes, using the same clock, we are generating the DQS generation, which is used during the read operations. So that means essentially entire circuitry is based on the single clock, that is in earlier generations of the LPDDR. Now coming to, so if you look at LPDDR4, both the clock signal and the data strobes operate at maximum rate of 2133 megahertz. So the clock and DQS, since DQS is derived from clock, both are operating at same frequency. Okay. The command address was sampled at the positive edge of the clock, is only sampled at one edge of the clock. Whereas DQ was sampled at both positive and negative edge of the clock. So that is where CA will be transferred at 2133 megabits per second, that is single data rate. DQ will be transferred double data rate, which is 4266 megabits per second. CA bus is a single data rate bus. Data bus is double data rate, making the maximum effective data rate on data bus as 4266 megabits per second. Data strobes are implemented as a differential pair and are bidirectional. Coming to LPDDR5, the clocking scheme has been changed. So two different pairs of differential signals, that is unidirectional signals. Okay. One for right clock, one for RDQS. Right clock WCK is used during the writes, RDQS is used for sampling during the reads. And these are unidirectional, but they are differential signals, but they are unidirectional. Whereas earlier the DQS used to be bidirectional. If you go back to the previous slide, you can see DQS used to be bidirectional. One going from host to device, that is WCK, other going from device to host, that is RDQS. In a few special cases, RDQS acts as a bidirectional signal. An LPDDR5 device uses WCK to capture the right data from the host. So when WCK comes, so it uses this WCK signal to capture the data from the coming from the host, and it also uses the same WCK to generate the RDQS and push out DQ on read from the device, on the reads from the device. So here what is differing is, though we are using the same source clock and WCK, but here the circuitry is differing. So we are not using the clock signal to generate the DQS. So we have an independent path, which is clock is running on a different frequency, WCK and RDK are working on a different frequency. So that kind of isolates the clock and WCK relationship. So clock can be worked at a different frequency, can be worked at a lower frequency, and WCK can be worked at a higher frequency to get the better data throughputs. Because when you are generating address and command, you don't need very high clock frequency. And LPDDR5 also makes the address and command sampling double data rate. So whatever we would do with earlier with X clock now can be done with X by 2, because you are able to issue commands at both positive and negative edge of the clock. So the new clocking architecture allows deep decoupling of the traditional clock signal, that is CK signal, from the host to device and data strobe signals. CA bus is sampled on both the edges of the clock. And LPDDR5 6400 requires CA transfer rate of 1600 Mbps. So for that, since you are doing double data rate for command address bus, so the clock need to only run at 800 megahertz. The new maximum rate of WCK RDQS in LPDDR5 is 3200 megahertz. The transfer rate it will give is 6400 megabits. The final rate of clock is CK is 800 megahertz. See, we are able to completely decouple. The clock is running at a different frequency. My WCK and RDQS are running at a different frequency. So here the clock is shown running at 800 megahertz. Command address bus is being sampled at both positive edge and negative edge of the clock. So that will give 1600 megabits per second. And WCK running at 4 times the frequency. See, in one clock period, you are having 4 edges of the WCK. So that will automatically give you 3200 megahertz. RDQS also at same frequency. DQ is sampled at both positive and negative edge of the clock. So hence you get 6400 megabits per second transfer rate. So essentially the new clocking scheme decouples the CK from the other clocks, WCK and RDQS clock. The challenges, there are some challenges due to this decoupling because they are going independently. So there is a specific synchronization that is required. So let's understand what are the challenges due to decoupling of clock from the WCK. LPDDR5 SDRAM requires internal synchronization of the clock and WCK. So inside the SDRAM, this synchronization is required in order to process any data transfer to and from the device. Because command and address is coming on CK, data is coming with respect to this. So there is a synchronization risk required between these two so that data is sampled properly. Synchronization of clock to WCK takes several clock cycles, which is penalty involved in performing the synchronization operation. So there are two things you can do. Either you always keep the synchronization on, but at the cost of additional power consumption. Second is you do the synchronization off whenever the writes and reads need to be done, then you perform the synchronization. But that will come with a penalty of several clock cycles. It will be advantageous to avoid this whenever possible, the synchronization. So that means when you intend to do back-to-back writes, so you keep the synchronization on. When the controller knows that it is not going to issue any writes or reads, it can turn off the synchronization. A specific sequence is required for how WCK must behave for synchronization to occur. So that we'll discuss in the synchronization topic, starting with static accession for at least one clock cycle. So that WCK should be static asserted for one clock cycle and followed by one CK of half rate activity. So there is specific static accession, half rate, it should run at half rate, then at the full rate. So it is like you have a WCK clock, sorry, the CK clock, which is running at 800 megahertz. The CA is sampled at this level. Once you issue the command, uh, synchronization command, so WCK has to run at clock kind of frequency. It is okay, static mode, static accession. After that, it has to move to the half rate for a specific amount of time. Then it can move to full rate. So that is the penalty that is involved in the synchronization process, followed by variable number of clocks of full rate activity based on the operating frequency. So this is where it is running at 3200 megahertz. Two options for synchronization of the clock and WCK. One is free running mode. That is the easy option. Synchronize the signals once and then keep WCK running constantly to maintain the synchronization. The drawback is what? It comes with increased power consumption. Second is what? System turning off WCK whenever it isn't absolutely required. This requires resynchronization of the WCK to CK before any data transfer can occur, whatever we have seen in the previous slide. So the memory controller will need to be clever in how it schedules the command. So the synchronization operation does not add unnecessary latency. So the memory controller need to have that that intelligence to know when the synchronization. I mean, in which scenario I need to turn off the synchronization and which scenario I need to keep the synchronization on. Uh, High speed internal clocking, okay, is one more challenge. Decoupling of clock and data strobe affects not only the interface between host and device, it also affects the interface of the LPDDR5 controller and LPDDR5 inside the host. The host side, a controller and PHY communicate with the external memory. So the host side, you have got both the controller and the PHY communicating with the external memory. Uh, the interface between controller and PHY is commonly implemented using DFI. So the data interface between the host and device is running at maximum rate of 3200 megahertz. The interface between controller and the PHY runs at 800 megahertz. even while the LPDDR5 runs the data interface to the memory at 3200 megahertz. This is referred to as DFI 1:4 ratio. The interface between controller and phi is running at 800 megahertz. The phi and the memory is running at 3200 megahertz. That is called as DFI 1:4 ratio. This is something we'll discuss as we go forward. This is just to give you a overview of what is majorly changed. I mean, this is what is going to impact a lot of the uh, features of LPDDR5. So LPDDR4 uses DFI 1:2 frequency ratio. The controller to phi clock will be running at 1066 megahertz, and the phi to LPDDR4 SDRAM running at 2133 megahertz. That is 1:2 ratio. So this shows that high speed clocking, where you can see the controller. You have got the controller, the control registers, and the other thing, and the DFI, the interface between the controller and the phi running at 800 megahertz with 128-bit interface. The interface between the phi and the device is running at 3200 megahertz. Only the clock domain running at 800 megahertz, but this WCK running at 3200 megahertz with 16-bit interface. The CA interface between host and device running at maximum rate of 800 megahertz. The DFI 1:1 frequency ratio is used for LPDDR5 commands. 1:4 frequency ratio is used for the data. This new mode of LPDDR5 controller and LPDDR5 interoperation is known as 1:1:4 frequency ratio. 1:1 for commands, 1:4 for the data. Next, the second thing is lower speed clocking options. LPDDR5 standard provides option for lower speed operation to reduce the power consumption. First option is ability for the CA bus clock rate to adjust when lowering the data strobe and data transfer rates. Once the data transfer rate drops to 3200 megabits or slower, it is possible to change the ratio, the CK to clock ratio, from 1:4 to 1:2, allowing the user to keep CA transfer rates at 1600 megabits per second, while data transfer rate is slowed to 3200 megabits per second. I mean, when you don't need the high throughput. So that is also possible, where clock is still running at 800 megahertz. The command address bus is sampled at with 1600 megabits per second. Now the WCK frequency can be reduced to 1600 megahertz, where RDQS also will be running at same frequency. The DQ transfer rate will happen at 3200 Mbps. Here the new clocking scheme has a clock WCK ratio at 1:4, DFI interface ratio at 1:1:4. If CK WCK ratio is 1:2, DFI interface ratio will be 1:1:2. The DFI frequency ratio for data operations change to either 1:4 in the case where the SDRAM data transfer is greater than 3200 megabits per second, or clock WCK ratio is 1:4. It changes to 1:2 in the case where transfer rate is 3200 megabits per second or slower, or the clock ratio is 1:2. This adjustment of DFI operating frequency ratio allows the LPDDR5 controller and DFI domain portion of the LPDDR5 to run up to 800 megahertz for any speed of operation, keeping the latency through the internal LPDDR5 controller and phi as low as possible for all speeds of operation. So in any case, whether when you are reducing it to 1:2 also, this frequency doesn't come down. It continues to be 800 megahertz. The one more enhancement that happened is the differential single-ended and strobeless operation. This is one more major improvement. In LPDDR4, the signals were always used to be differential, whereas uh, the LPDDR5 allows signals to be operated in single-ended mode, or in some cases strobeless operation also. So during high-speed operations, LPDDR5 device uses clock, WCK, and RDQS in differential mode. Means you have clock underscore T, clock underscore C, WCK underscore T underscore C, RDQS underscore T underscore C. This differential mode will provide maximum performance. LPDDR5 has some built-in power saving features for use cases requiring low performance. So when you need when you are okay with low performance, some power saving features capabilities have been implemented. One of them is ability to change these three differential signals into single ended signals. That means you don't need to provide the differential mode when running at data rates at below or lower at or below 1600 mbps. There is also one more mode called as strobeless mode. Place the clock and WCK in single-ended mode operation. Turn off the RDQS entirely. Intended for low-speed operation, and it requires LPDDR5 to generate an internal strobe to capture the read DQ from the device. So when you are in strobeless operation, 5 has to generate internal strobe to capture the read DQ. When switching clock, WCK and RDQS from differential to single-ended mode of operation or strobeless mode, it is required to disable the device termination for clock, WCK and RDQS as well as to the CA, DQ and DMI signals. So this is the penalty of switching from differential to single-ended mode. So this table shows what are the allowed combinations for clock, WCK and RDQS. If you are operating more than 1600 Mbps, everything has to be in differential. If you are operating less than 1600 Mbps, it can be differential, it can be single-ended, clock can be single-ended, WCK can be differential, RDQS can be differential, or everything can be single-ended, or it can be single-ended, WCK can be single-ended, and RDQS can be disabled. So these are the different possible options for differential and single-ended and strobeless operation.